Welcome back. This is lecture 16. So let's continue our discussion on thermal noise, and let's start off again with the simplistic RC network that we were discussing in the previous lecture. So again, let's say this is an RC network, and this is a signal source, and I want to find out the uh, noise at the output, or rather, I would like to find out the uh, uh, equivalent circuit which captures both the signal and the noise for the output, and from there I would like to deconstruct the noise and the signal and then move forward, right? So the total circuit is your input remains as is, but I understand this R that we have here is noisy. So for the purpose of our circuit analysis, we are going to replace that noisy R with a noiseless R and a voltage source in series, or you could have as well done a noiseless R or a current source in parallel, equivalent current source in parallel. So let's do the voltage source in series. This is Vn, right? Rest of the circuit remains the same. This is V0, and then we wanted to then the analysis that we did at the end of the previous lecture was to find out the noise power spectral density at V0. And in order to find out the noise power spectral density, what did we do? For noise, we simply desensitize the input, the signal input, and we only did a noise analysis. Vn, this is R, and we are taking the output on the capacitor, across the capacitor, and since there is nothing other than the noise source, the voltage that I am going to uh, uh, observe on the capacitor is basically the noise voltage, and we found that the spectral density, the power spectral density of the noise voltage is P and O was essentially 4 kTr, that is the power spectral density of Vn divided by essentially 1 plus omega square r square c square, right? This is where we stopped in the previous lecture. What about the effect of signal? The effect of to find the signal. So for signal analysis, we basically desensitize the noise source. Now again, this is all a part of the analysis. In reality, you will never be able to desensitize anything. All of them appear together. But since this is a linear time invariant network, or more particularly in this case a linear network, I can impose superposition and I take one source at a time. So what is your V0 signal? So our uh, is V0 signal is basically uh, whatever is the power spectral density of the input, right? So this is SV in divided by, again, the transfer function, it is 1 plus, I multiplied by the transfer function, which is transfer function squared in this case, which is 1 plus omega square r square c square, right? Note that all these are we are squaring it because ultimately it's a power spectral density, right? We are basically taking the h of f and we are doing mod h of f whole square, right? Okay. So now, before we move forward, the part that we need to understand is, what do we really care about? when we say that we want a circuit to be of low noise, what do we actually mean? One might argue that the easiest way to get rid of noise is to basically short the output capacitor, right? If I short the output capacitor, there will be no noise across the capacitor, no noise voltage across the capacitor. But we all understand that's not the right thing to do, right? Why? Because we'll also lose the signal, right? So in essence, we are not, the correct definition of a good noise circuit is not the one that reduces noise, it's the one that reduces noise without affecting the signal strength, right? So for a given output signal strength, I would like to reduce noise. So what is a better metric to characterize uh, two circuits with respect to noise performance? A better metric is not to only analyze noise, but to analyze noise in the presence of the same signal strength. In other words, we are looking for the ratio of signal and noise, right? So we are more interested in signal to noise ratio, or SNR, which is basically the signal strength at the output divided by, or rather the power spectral density of the signal at the output divided by the power spectral density of the noise at the output, right? That's what we wrote as SVN, right? Because it's all voltage. Okay. So what will this be? Note that both in the case of signal and noise, the denominator in this particular example is the same. So I essentially get the signal power spectral density at the input divided by 4 kTr. Okay. So in order to maximize the signal to noise ratio, what do we need to do? We basically need to reduce R, right? Obviously, I can increase the strength of the signal, that I can always do, but often the strength of the signal that comes to the circuit, given circuit, is not in your control. If it is not in your control, all you can do is that for the given strength of the signal, you have to reduce noise. So in this case, it seems like we'd like to, the only way to go about doing that is by reducing R, right? But what is an RC circuit? It's effectively a filter, right? So if you reduce R, I am changing the bandwidth, isn't it? If I am reducing R, I am changing the bandwidth. So that essentially changes the way the circuit itself works. But let's say I do not want to change the transfer function, right? What is the transfer function? The transfer function for the first order RC circuit is 1 by 1 plus j omega RC. If I do not want to change the transfer function, but I want to reduce R, then what should I do? I should increase the capacitance by the same factor, right? So what I'm saying is your h of f in this case is 1 by 1 plus j, should I write h of j omega, because in today's lecture we are dealing in omega domain just to keep the number of terms under control, right? So we understand that from this, we understand that reduce R by 2x to increase SNR by 2x, right? But reducing R by 2x impacts the transfer function itself. But if we do not want to impact the transfer function, what is the next thing to do? Increase C by 2x to ensure h of j omega is not affected, because ultimately I do not want to change the transfer function of the signal, transfer function of the circuit. I only want to improve the noise performance of the circuit, right? What did I essentially do? I took this. What does it mean when I am reducing R and increasing C? So, let me get rid of the input source for the time being, because that is of no consequence as of now. So this is R and this is C. And in the example that we did, that we just did, what did we do? We basically changed this R to R by 2, and we change this C to 2C. Correct? So what does it essentially mean in circuit parlance? Another way of thinking about it is, you take the same circuit that we had, we take the same circuit, copy it, right? Copy it, and then connect it in parallel to the original circuit, node by node, right? Connect this in parallel to the original circuit, right? So if whatever you get after connecting it, right, you take the circuit, copy it, slap it on top of the original circuit and connect it in parallel, whatever you get is essentially the impedance scaled version of the original circuit. And in the impedance scale version, R has reduced by a factor of 2. In this case, because I have essentially done this, I have essentially copied it once and connected in parallel. So R goes down by a factor of 2, and the C goes up by a factor of 2. So essentially there is no change in transfer function, right? If we take the same circuit, copy it n number of times, and connect them node to node, then obviously there is no current flow through any of the wires that connects these two circuits. I mean, when I say there is no current flow, what I essentially mean is there is obviously an input associated. So let's say the port remains as is. Okay, so obviously the current through these colored wires are all 0, right? The signal current through all these colored wires are all 0, because all the nodes for the circuit on the left and the right are are of uh, are of same potential, right? Okay, so in order to be truly connecting it by node to node, I should also connect the input, right? Okay, so the current through all the colored wires are essentially 0, right? Which essentially means that the transfer function of the circuit will remain the same even after uh, after connecting them in parallel. Okay, so which now this, there is a technical term for this. This is called, this type of copying the circuit, copying them and putting them on top of each other, this is called impedance scaling. This is called impedance scaling. So if you do impedance scaling, impedance scaling can be done in many ways, right? In one case you can reduce R, in another case you can increase R. But if you do an impedance scaling of a circuit in such a way that the R, you reduce the lossy elements, then from this simplistic example you see that the signal to noise ratio improves, right? So impedance scaling in principle, right? Even though I'm not, I just took a toy network to show you. In principle, can be shown that impedance scaling by copying the network and pasting the same network over the original one will always reduce noise, keeping the signal strength constant, or in other words, it will increase the signal to noise ratio. Okay, but what is the cost? Obviously the cost is what is the power that you are drawing from the source. What is the power that you are drawing from the source? If the power that you are drawing from the source is essentially the power that is getting dissipated across in the R. So right now, if you had a single network, right, the power that was dissipated in the R would have been whatever the I squared times R, right? So this, if this is I, so this is also I. So essentially the power that you have dissipated from R, essentially the current that you are drawing from the source, or the power that you are dissipating in the R, is essentially doubled, right? So the penalty is that of power consumption. So impedance scaling increases SNR, but increases power also by the same factor. Okay, so in a very layman's language, one might say that if you want to buy signal to noise ratio, you have to pay with power. Power is the currency through which you buy signal to noise ratio, right? So if you, let's say you have some signal to noise ratio of 20 dB, you want to increase it, you want to double it, right? That is, I want to go to 23 dB. If I was, let's say, burning 1 milliwatt of power, all I need to do is take the same circuit, copy it once, and then put and connect these two circuits node to node in parallel. I will automatically have, without any effort, increase of signal to noise ratio to 23 dB. However, now I am going to spend 2 milliwatts of power, right? This is one simple way of increasing the signal to noise ratio. But sometimes we might not be in a position to spend double the amount of power. So in those cases, we'll have to think of some other ways of reduction of noise while keeping the signal constant. Okay. Okay. So the next thing that we'll focus on is what happens if you have more than one resistors in a circuit, that i.e. that if you have more than one noise producing elements in a network, right? So what I'm basically saying is, let's say you have a network which has one port across which you have a resistor connected, you have another port across which you have another resistor connected. I call this R1, I call this R2, and you are probably taking the output from another port. And you have inside this box, you have all noiseless elements, that is only L's and C's. Okay, no resistors inside. So inside this box is the noiseless box. Okay, and you have noisy resistances at the ports. Okay, so what is the usual thing that we are going to do? We are going to replace these noisy resistances with their equivalent noise equivalent, noise, or rather noise source equivalent. This is R1, this is R2. I call this Vn1, I call this Vn2. Okay, I want to find out what is the total noise at the output. right? So what is the usual way of going about doing it? I'll basically find out, again using superposition, right? I'm going to find out the transfer function from input to the output, or rather from the noise port to the output port, through by desensitizing the other noise source, right? So we have desensitized this noise source, no noise source here, and I'm going to find out the output noise in experiment 1. I'll do this is experiment 1. In experiment 2, I'm going to desensitize the noise from R1 and have the noise from R2. Here no noise source. This is experiment 2, and I'm going to combine the effect of VON1 and VON2, right? Let's say the so what will be the total output noise? So combined noise is VON1 plus VON2, right? And this is in time domain. We are, I mean, right now this experiment we are all doing in time domain, correct? Okay. So now if I have to find out the root mean squared noise, because ultimately that's what we are, or rather mean squared noise, because ultimately that's what we are interested in. So if I have to find out the mean squared noise, the mean squared is basically sigma squared VNO. So what should I do? I should basically find out the variance of the total noise at the output, which is essentially I'll do VON1 plus VON2 whole squared and take the mean of that. And I'm not subtracting the mean of this because it's a, I mean both VON1 and VON2 are zero mean signal, right? So only squaring and taking the average of the square is sufficient. So uh, so if I square this, what do I get? I essentially get the variance of VON1 squared. So basically sigma squared VON1 plus sigma squared VON2 plus I get the expectation of, or rather I basically get 2 VON1 VON2 and the average of that, okay, or the expectation of that. Now note that VON1 and VON2 are uncorrelated, right? So since VON1 and VON2 are completely uncorrelated, what is the expectation of VON1 times VON2? This is basically 0, right? So this goes to 0. So then what do I get? I get the variance, the total variance is essentially the individual variance, the variances that I got from the individual experiments, right? So this is the variance from experiment 1 and this is the variance from experiment 2, right? So what is the key takeaway then? The key takeaway is I can effectively do the noise analysis in the power domain, because noise essentially I'm doing squaring, so essentially I'm doing in power domain. So I can essentially use superposition principle in the power domain as well when when I am considering noise from different sources, right? So in essence, if I have noise from n different ports, I can do the noise analysis for each of those ports and find out the power spectral density or the variance at the whichever analysis you are doing at the output, and each of those experiments will lead to a result. And we understand that when all the noise sources are combined together, the total output noise will essentially be the summation of all those individual analyses, right? Okay, so that eases our analysis quite a lot. uh, but there is another thing that would essentially ease our analysis. So let me formalize this first. So this essentially is telling us that if I go into the power spectral density domain, so then SVNO is essentially SVN1 plus, or SVNO from the noise source 1 plus SVNO from the noise source 2. If you have n number of noise sources, you basically sum up the power spectral densities from each of those uh, contribution of power spectral densities from each of those noise sources. Okay, I'm not breaking the ports out, but let's say I have a network with n different resistors and inductors and capacitors and so on, and here I am taking the output. So what would be the method that I would follow? I would basically have a noise source associated with each of those resistors, and I'm going to find out the transfer function from each of these resistor to the output, right? And then multiply the transfer function with the, the power spectral density for each of the resistors, and then sum up everything to get the output noise, right? So essentially what am I doing? I'm basically saying, let's say this power spectral density, if I say that this is VNO, is basically the summation of the power spectral density of, let's say this is the first resistor, this is the kth resistor. Let me move all these complications, and let's say this is RK and it has a noise source associated with it, right? And let's say the the transfer function from this noise source to the output is h of k, right? H of k times j omega. So the contribution or the noise contribution from the noise from RK is essentially 4kt times RK times mod of hk square, right? Hk j omega square, right? So this is the contribution from the kth resistor. If you have uh, n number of such resistors, you will essentially do 4kt R1 times mod of H1 whole square plus 4kt R2 plus mod of H2 whole square, and so on. So essentially what we are doing, we are basically summing over, I should not use k because this becomes an abuse of notation in the presence of Boltzmann's constant. So let me use m. M equal to 1 to whatever, 1 to n, right? So this is essentially what we have done till now. But note that this requires If you do by hand, this requires us finding out transfer functions. If there are if there are 10 registers at different parts, I have to find out the transfer function from each of those n registers to the output individually. So basically, uh, 10 transfer function calculation and then doing this summation. Right? If I have 100, then you have to do 100 transfer function calculation and then the summation. And I mean, you might say why should I do it? I can do it using simulator. In place of you, the simulator has to do that calculation. And if your network has million registers, then one has to do, the simulator has to do a million different transfer function calculations, and quickly this can blow up. So what Nyquist long time back figured out is that there is a way of simplifying this problem by using our good old reciprocity theorem, and that is what we are going to see next, right? So what we are going to see is, so let's say I I look at this. If I stare at this equation for some time, I can basically say that this is equal to 4kt times summation of Rm times Hmj omega squared, right? So again, Rm is value of the resistor, but what is Hmj omega? Hmj omega is the voltage transfer function from the resistor, from a voltage source associated with the resistor in series to the final output. Okay, but if I draw your attention to the good old reciprocity theorem that we learned in our undergrad days. So what does it tell us? So it basically tells us that, let's say I have I'm taking the mth branch in this case. I'm taking the mth branch out. This is Rm, this is Vm, and I have this, all the rest of the resistors are here. Everything is same, just that the Rm I have pulled out. Okay. So what does reciprocity tell us? If the transfer function, the voltage transfer function from this port, the voltage transfer function from this port to this port is Hm, then I can basically copy the same thing and desensitize uh, or short the voltage source and apply a current source at the output of value 1 angle 0, that is phasor 1 angle 0. The current that I am going to see here, if this is 1 angle 0, the current in this direction going from top to bottom that I am going to see is also equal to Hm, right? So this is by use of reciprocity. Okay. Okay. So how is this useful? This is useful because now note that what is the power consumption in this under this new setup? Under this new setup in figure B, what is the power consumption across the resistor Rm? So P Rm is essentially I squared Rm. So essentially mod of Hm j omega whole squared times Rm, right? So now I think we are going somewhere because this is of the same format as this on the top, correct? So now can you tell me what is the uh, So let's say I have this, let's say this is R1. What will be the power consumption across R1? The power consumption across R1 will be H1 square. That is the transfer function from the current source to R1 times R1 square, right? So what does, so then what is summation of Hm j omega square Rm mean? This is the total power dissipated in the network. Correct? So to now connect the dots, we know that our total noise power spectral density, right, in the presence of all the noise sources together is 4 kT times this summation, right? And what is this summation? This summation is nothing but the power dissipated in the network in the reciprocal circuit. Correct? So SVN out in original network is equal to 4 kT times power dissipated in the reciprocal network when 1 angle 0 current source is applied at the output port. Okay, so this is neat, but we are still not done, because if you recall, from one of the earlier networks or one of the earlier lectures, you have a network and I am driving it with any current source or a voltage source. If it's an LTI network, any LTI network, right? Can I relate the power dissipation to the terminal characteristics of the network? Yes, I can, because I know that if the Z, if the impedance in this network is Zin, then I know that power dissipation is also equal to the current, that is 1 angle 0, in this case angle doesn't matter, 1 times real part of Zin. Correct? So which essentially means that my SVN out, I can relate the total output noise or noise spectral density in the original network would be 4 kT times the real part of Zin of the reciprocal network when looked through the output port. Okay, so let's do a quick example. The example that we have already done, we can redo that. So let's say we have this resistor capacitor network. I want to find out the power spectral density across the capacitor, right? So what should I do? I need to find out Zin. What is Zin? In this case, it's basically one R and one capacitor in parallel, so which is nothing but R times 1 by j omega c by R plus 1 by j omega c. In other words, Zin is R by 1 plus j omega rc. Note that this is a complex impedance. So if I deconstruct it into a real part and an imaginary part, I'm going to get real of Z in to be equal to R by 1 plus omega square R squared C squared, which means that my the is VNO is 4 kT times real part of Z in times R by 1 plus omega square R squared C squared, which is exactly the expression that we had gotten in the previous in the brute force method, right? But I mean, this is not really useful for only one resistor case. If we have, let's say, 2 or 3 resistors together, so let's say I have a case in which I'll show a simplified case maybe. So let's say I have a series parallel combination, right? It's a resistor ladder, let's say, and I say uh, this is R, this is R, this is 2R, this is R, this is 2R, right? And I am interested in finding out the power spectral density from this node. I am observing here. I want to find out the power spectral density looking in, right? SVNO. So if I had to stick by the old process, what did I have to do? I had to find out the transfer functions from each of these resistors to the output and then sum them up and multiply them by 4 KTR, right? So since I have 1, 2, 3, 4, 5 resistors, or maybe I can simplify it and get to 4 resistors, so I have to find out 4 different transfer functions. But I don't need to do that now. All I need to find out is the equivalent impedance, and in this case there is no imaginary part, then 4 KTR, 4 KT times the equivalent impedance. What is the equivalent impedance? Looking into this port, I know that looking, if I remove these ones, so note that this R and this R becomes 2R, this 2R and this 2R comes in parallel, becomes R, that R and this R becomes 2R, that 2R and this 2R comes in parallel. So I essentially get the equivalent Thevenin impedance is R, right? So Z in is equal to R. So my SVNO is 4 kT times R, right? So that is the power of this finding out noise spectral density from the method that Nyquist gave us about 100 years back, right? So in today's lecture, so what did we learn? We found that if I have to increase the signal to noise ratio, right? Firstly, the signal to noise ratio is a parameter of interest, not noise only, right? But if I have to increase the signal to noise ratio, what I have to do? I have to do impedance scaling, right? If I do impedance scaling by, which essentially means that I take a circuit, make a copy of it and connect it to the original circuit node by node, I'll simply find out the SNR has improved by a factor of 2 or 3 dB. Okay. But what is the cost that we pay? The cost is that of power, right? The power will also double. Then next thing we saw, our next analysis that we did was to find out how do I do a noise analysis when we have multiple noise sources in a linear time invariant network. We saw that I can effectively use superposition in the power domain also when we are doing noise. So that is, I can find out the noise transfer function from each of these noise sources to the output, and then and sum them up as if the others were each one of them individually, assuming the others were noiseless, and that will eventually get to our that will give us our total noise spectral density. But then we saw that that is also probably a very tedious thing to do if we have significantly large number of noise sources. Then we found out found out a way of, or looked into, we didn't find out, Nyquist did it for us 100 years back. We looked into one of these noise theorems where we could relate the spot spectral density of the original network to the power dissipation of its in its reciprocal equivalent, when the reciprocal equivalent output when a 1 ampere current source is being used to drive the terminals of the original network, right? To terminals of the reciprocal network which corresponded to the output terminals of the original network. And then we didn't stop there. We also found that ultimately, after doing some network tricks of power dissipation, we could relate the power spectral density to the terminal real part of the terminal impedance of our so we could relate this to the real part of the terminal impedance of the reciprocal network, and that is essentially the crux of this noise theory till whatever we have done till now. But before we stop here, the caveat that you must understand is this equivalent, right? This equivalence only holds for a perfectly LTI network with only having RLs and Cs, because this relationship where I am relating the power dissipation within the network to the effective noise is only valid if you do not have any control sources within the network, right? This is only true if only for RLC networks, right? Okay, this is only true for RLC networks. This will not be true if you have control sources. Okay, okay.